So in the previous videos, we showed that if we have this form of a quadratic trinomial, which we'll later refer to as vertex form, we can come up with its graph fairly easily. Unfortunately, we typically don't have that form, and we instead have this form, which we'll later refer to as standard form. So there's a bit of a problem. Fortunately, there's a solution. There's this process called completing the square, which allows us to go from standard form to vertex form. And in the last video, we spent a bunch of time doing exactly that. We first learned about these puzzles that kind of taught us the method for completing the square, and then we used that method of completing the square, I think 4 different times to go from standard form to vertex form. Again, starting in standard form, we produced this vertex form, this standard form produced this vertex form, and finally this standard form produced this vertex form. It's a hard enough process that it's kind of easy to get lost in there and forget why we were doing what we were doing in the first place. The goal was to come up with the graph of this equation right here. The way we'll do that is we'll first rewrite it in vertex form, and then we'll recognize that really this is just transformations of x squared. We have 2 different vertical transformations corresponding with this 2 and this -7, and 1 horizontal transformation corresponding with this +2. Since there's multiple vertical transformations, the order we apply them is really important. Since we multiply before we add and subtract, it makes sense to first multiply all of the y values by 2, and then subtract 7 from all the different y values. Since there's only 1 horizontal transformation, it doesn't matter when we do it. And since the horizontal transformations are kind of the opposite of what you might think, instead of adding 2 to all of the x values, we're going to subtract 2 from all the x values. So in the first video, we learned how to go from vertex form to the graph. In the second video, we learned how to go from standard form to vertex form. In this video, we're just going to do the entire process. We'll start out with something in its standard form. We'll complete the square to turn it into its vertex form. We'll look at that vertex form and recognize the transformations, and then we'll apply those different transformations to come up with the graph. We could do that with this example, but I kind of want to start from scratch and go through the entire process. So here is a function that we want to graph. We refer to this as a quadratic trinomial in its standard form. Kind of a mouthful. The way I want you to come up with the graph of this thing is to first get it from standard form to vertex form. The way you do that is by completing the square. You might notice that this one is written in function notation. Since we're going to be messing with both sides of the equation, it's a little bit easier if you replace the f of x with a y, just because it's easier to do algebra when you have a y floating around as opposed to an f of x. So while you don't have to do that, it's a little trick that you might want to consider. Now our first step is always to isolate the x and x squared terms. So we're going to subtract 30 from both sides of the equation, yielding y minus 30 equals 2x squared minus 16x. Now is the step where we kind of check our leading coefficient and make sure it's a 1. In this case, it's a 2, which is problematic, but it's got an easy fix. All we got to do is divide both sides of the equation by 2. When we divide the left side by 2, we get y minus 30 divided by 2. When we divide the right side of the equation by 2, we can divide each of these coefficients by 2, giving us x squared minus 8x. Our next step is to add some number to both sides of the equation so that we end up with a perfect square on the right-hand side of the equation. In this specific case, that number is 16. Where that 16 came from was half of this -8 is -4, and -4 squared gives me this positive 16. We'll ignore the left side of the equation for now, so we'll leave this as y minus 30 over 2 plus 16. And on the right-hand side of the equation, we'll recognize that because we followed all these steps above, we've produced a perfect square. That perfect square in this case is x minus 4 squared. So we'll change this x squared minus 8x plus 16 into x minus 4 squared. At this point, we're just about done. All we got to do is solve for y. The first step in doing so would be to subtract 16 from both sides of the equation, leaving us with y minus 30 over 2 equals x minus 4 squared minus 16. Our next step is to get rid of this 2, so multiply both sides of the equation by 2. On the left, that leaves us with y minus 30, and on the right, make sure that the 2 hits each of your 2 terms, leaving us with 2 times x minus 4 squared minus 32. Finally, to get the y all by itself, all I got to do is add 30 to both sides. On the left, I just have y, and on the right, I'd have 2 times x minus 4 squared minus 32 plus 30, in other words, minus 2. We went from the standard form that we do not know how to graph into this vertex form that we're pretty comfortable graphing. While it doesn't specifically ask us to do so, it's not a bad idea to list out the different transformations that allow you to graph this guy. So there's two different vertical transformations, one corresponding with this 2 and one corresponding with this negative 2. And there's one horizontal transformation corresponding with this negative 4. The first vertical transformation is applied by multiplying all of the y values by 2. The second vertical transformation comes from subtracting 2 from all the y values. And the one horizontal transformation that I have, which comes from this negative 4, tells me to add 4 to all of the different x values. Well, it doesn't matter if we apply the vertical transformations first or the horizontal transformations first, because there's two vertical transformations. I'm going to get those out of the way. I apply them by multiplying the y values by 2 and then subtracting 2 from that product. So these 2 points that have a y coordinate of 4, when I multiply them by 2, they move up to 8. And when I subtract 2, they end up at 6. So A and E, after the vertical transformations, will be at these two dots. These points at B and D each have a y coordinate of 1. 1 times 2 is 2, and 2 minus 2 is 0. So the points B and D will end up at these two dots right here. And finally, this point C, that was the vertex of my original graph, has a height of 0. That 0 times 2 is still 0, and that 0 minus 2 is negative 2. So the vertex after the vertical transformations will end up down here at 0, negative 2. You could connect these guys with a parabola shape, but I'm not even going to bother this time because this isn't my final answer. For my final answer, I have to add 4 to the x coordinates of each of these different points. This point has an x coordinate of 2. 2 plus 4 is 6. So this point that started at E and then moved up here to 2, 6 is going to end up way over here at 6, 6. Similarly, this point that has an x coordinate of 1, because 1 plus 4 is 5, is going to end up over here at 5, 0. 0 plus 4 gives me 4, so the vertex will end up at 4, negative 2. Negative 1 plus 4 is 3, so this point that started out up here is going to end up over here at 3, 0. And finally, this point that started at negative 2, 4, and then traveled to negative 2, 6, when I add 4 to its x value, will end up at positive 2, 6. These 5 dots are all on my final transformed graph. I connect the dots with something that has roughly the same shape as I start out with in red, and that produces this final graph. There was no real prompt in this problem, but if the prompt was just to come up with the graph, well, I guess this is how we do it. But typically what will happen in these problems is you'll be asked to locate the vertex, which in this case ends up at 4, negative 2. The x-intercepts, which in this case are at 3, 0, and 5, 0, which we're lucky enough to just get from the graph, but as I showed in the previous video, we could also find by just figuring out what inputs lead to an output of 0. In other words, solving the equation f of x equals 0. To solve this equation, you could take this form of f of x, or it'll make your life a lot easier to take this form of f of x and solving for when that equals 0. So add 2 to both sides, divide by 2, take the square root, add 4, and I think you'll get these two solutions of 3 and 5. After you have the vertex and the x-intercept, the last thing left to find is the y-intercept. The y-intercept is just where we cross this y-axis here. Unfortunately, this doesn't show up in the portion of the graph that we have pictured, but we can solve it easy enough algebraically. Since we'll be crossing the y-axis when the x-coordinate is 0, and the x-coordinate is the input to the machine, to figure out the y-intercept, all we have to do is figure out what comes out when we put 0 into the machine. We can do that a few different ways. You can plug in zeros everywhere you see x over here, or what's even easier is to plug in zeros everywhere you see x over here. 2 times 0 squared minus 16 times 0 plus 30 is just going to leave me with 30, because the x squared term and the x term will always go away when you change the x's into zeros. Completing the square to get something into vertex form, looking at vertex form and applying the different transformations, taking your transformed graph and locating the vertex, the x-intercepts, and the y-intercept is everything that I want to get out of this section, so I'll end this video here.